Okay, so good morning, everyone. So welcome to the lecture number 4 of MoCaO Lectures series in 2024. And today's lecturer will be Dr. Isabelle Shankar. And Isabelle is an assistant professor in the Fabry-Bosch-Massit Department of Mathematics and Statistics at Portland State University. So she received her PhD in Applied Mathematics in 2021 from the University of California, Berkeley. She held postdoctoral positions at Illinois at Urbana-Champaign and the Max Planck Institute for Mathematics in the Science before joining Portland State University. So her research interests include algebraic geometry, convex optimization, and combinatorics. So today she will give a lecture on the duo of a convex body. So over to you, Isabelle.
Yeah, thank you for that lovely introduction. So yes, I'll be talking about the dual of a convex body. In particular, let's see. So I'll motivate it a little bit. Why we might be interested in such a thing, and I think it's been hinted at and discussed a little bit already, but I may repeat a couple of things that Vera has already mentioned. So bear with me if there's a bit of repetition, but I'll try to motivate why we might study this object. And then, of course, define it. I'll also talk a little bit about conic duality, so essentially the same type of thing, but in the cone case. And then if there is time at the end, I'm going to talk about two places where this kind of duality appears. Now, this is by no means an exhaustive list. Cone factorization and then the facial structure. These two topics aren't an exhaustive list of all the ways in which convex duality appears. It's just two particular topics that I find interesting and I think are nice examples of where we see the dual of a convex body. So that is the plan for today. So as motivation, of course, we will turn to optimization. So here we have just a standard optimization problem in Rn. We want to maximize our function f over Rn, subject to some constraints, right? So x has to be in some set S. There are, of course, many different questions we can ask given some optimization problem. Two that I'm particularly interested in are going to be, how do we certify that what we have when we have some solution is actually optimal, right? So suppose you give me an optimization problem, I give you an X, and I say, hey, this is the best one. This is truly a maximizer. How can I certify for you that that truly is optimal? And then the other question really has already, I believe, been answered, but I'll just briefly refresh your memories on that when we get to it, which is what's the geometry of the collection of maximizers? And of course, you know, we're working in convex geometry here, right? So we're going to restrict ourselves to convex optimization problems. So here our objective function is going to be a linear function. So we're maximizing a linear function subject to a convex set. So our feasible region will be convex. In fact, it'll be a convex body. So that's sort of the context I want to start with. So let's talk about that first question, right? How do we certify optimality? Well, again, here we have our convex optimization problem, maximize a linear function. So here we're taking a linear functional A, taking the inner product with X, where X comes from a convex body, C. What I mean by convex body is that it's a compact convex set with non-empty interior. And so that's our convex optimization problem. I'm restricting to convex bodies just because things are a little bit cleaner. It's not too bad to think about things more generally for convex sets, but the compactness just makes things, frankly, a little bit nicer. So I'm just trying to make things a little clearer for today. So we'll restrict ourselves to convex bodies. So to start, in terms of trying to certify optimality, I want to define the normal cone, which I think we may have seen already. But so given some point in our convex body C, so I'll call that point Y, we can define the normal cone of Y with respect to C as the set of linear functionals which are maximized at Y. Right, so here we're collecting all linear functionals where at the specific point Y, the inner product of L and Y is going to be greater than or equal to, right? So we're maximizing than the inner product of L with any other point in our convex body or any point in our convex body. Okay, so we're collecting the linear functionals that maximize at Y. And then why are we interested in this? Well, if we have a maximizer, right, what does it mean for a point in our convex body to be a maximizer? I mean, it really just means that we're satisfying this inequality, right? The inner product of A with any point in our convex body is less than or equal to the inner product of A again being the linear functional now specific to our optimization problem, not just any linear functional, but specifically the one that comes from our optimization problem. So the inner product of A with that maximizer must be greater than or equal to the inner product of A with any other point in our set. All right. I mean, we can really see now in almost immediately when we have this definition of a maximizer and the definition of our normal cone, how do we certify that X hat is truly an optimal solution? Well, we check that A, our linear functional coming from our objective function, is in the normal cone of X hat. It's an equivalent way of checking if we have a maximizer. And I just want to reiterate that if there are any questions, you can either unmute yourself and just yell at me. I'm happy to answer questions throughout, or post it in the chat, and I'm happy to answer any questions as we go. So, okay, so let's do an example. Examples are always really nice. Here's a quite simple one. Let's take the square, where I'm just taking the convex whole of plus or minus 1. What is the normal cone of the point 1, 1? So this is one of the extreme points of our convex set or our convex body, a square. Well, what are we asking? We're asking what are the linear functionals that attain their maximum at 1, 1. And it's really pretty easy to see what we get. So maybe let me go back to the definition of normal cone, right? What was our point? It was 1, 1. So we're really just asking, you know, what linear functionals, when we take their inner product with any point in the square, give us are less than or equal to. Remember, Y was the point 1, 1, so just the sum of the coordinates L1 and L2. And it's not too hard to see that you can really restrict to the extreme points to do this. So now we're really just asking for what L1, L2 in the dual space are such that plus or minus L1 plus or minus L2 are less than or equal to L1 plus L2. And that's just the row vectors, if you like, or linear functionals or vectors in the dual space, however you prefer to think of it, that are coordinate-wise non-negative. And so this is the normal cone. We can see right here, right? These are the linear functionals that maximize at 1, 1. So that's right, that's quite nice. So we have this description, this easy description of the normal cone. And so then if we're optimizing over the square, all we really need to do is check if our linear functional A1, A2 is in this normal cone, and that would certify optimality. So that answers our first question, right? How do we certify optimality given some maximizer? Now, the other question we had was, what is the geometry of the set of maximizers. And really, this has actually been answered already. So let me just remind you that the set of maximizers, again, in a convex optimization problem, right? So we're looking at a linear objective function over a convex body in this case. The set of maximizers are always going to be exposed faces. So if we have a particular linear function, there will be some exposed face of our convex body. So exposed face, remember, is a face that can be described as the intersection of our convex body with a hyperplane. So that hyperplane exposes a face. That's going to be our set of maximizers. So always an exposed face. Now, how does this relate to the normal cone, right? So we asked this question about certifying optimality, and it led us naturally to the normal cone. How do we connect this with exposed faces? And the answer is really through duality. So let me define what the dual to a convex body is. So given a convex body C, and for simplicity, I'm just going to assume 0 is in the interior of our convex body. Its dual is all the linear functionals in our dual space, such that their maximum is at most 1 over any point, over all points in our convex body C. Right, and I'll denote this by C circle. Now, I will note at this point, if for those of you who've already seen definitions of dual, this might be a little different. Some would call this the polar. And I'm going to call this the dual for today. Depending on what book you're, even standard books on texts on convex geometry will call these things slightly different things. It really kind of comes down to negatives versus positive, if we're maximizing or we're minimizing. But for today, this is the definition I'm going to use for the dual of a convex body. And then really, again, it's mostly just up to sort of negation. Good. Okay, so let's look at an example. Always definitions followed by examples. I think that's always extremely helpful. So again, let's look at the square. Nice, clean example, perfectly good. Convex body, compact, convex, non-empty interior, convex set, right? So what is the dual of the square? What is the dual of the square? Well, here we have just essentially the definition, right? So linear functionals, a1, a2, such that a1x plus a2y is less than or equal to 1 for points x and y in our square. And again, it's enough to consider the extreme points, so the vertices of my square. And so, and that's not too hard to see. I encourage you but for those of you who are watching this as a video, I actually encourage you to pause at this moment and maybe work out why you need just the extreme points. For those of you who are here live, it boils down essentially to convexity. So extreme points are sort of enough to look at. So at the plus or minus one points, we can see that the dual body is just defined by the 4 hyperplanes, plus or minus a1, plus or minus a2, are less than or equal to 1. And that's what I have drawn here in orange, overlapping, of course, the dual space with our R2. Here is another example, non-polyhedral this time, of a convex body. So on the left, we have what I call the racetrack. I think it's pretty commonly referred to as the racetrack. And on the right, we have its convex body, which we can see is sort of the intersection of 2 disks. So you'll notice here and in the polytope case, right, we started with a convex body, right, compact, non-empty interior convex set, and ended up with a convex body. And this is not a coincidence at all. This is sort of going to happen, assuming we have 0 in the interior of our convex body. As long as we have 0 in the interior, we're always going to need that. It plays a pretty important role from this perspective, from the construction of the dual of a convex body. So as long as we have 0 in the interior, then the dual of a convex body is itself a convex body in, of course, the dual space, which is really, really nice. Moreover, say we want to dualize back again, right? If we were going to take the dual of this object over here on the right, what do we get back? We get the racetrack. So this is called biduality. In general, we have biduality down here. In general, what we get when we take the dual of the dual is the closure of our original object. But if we started with something closed, then we can just say the dual of the dual is the original convex body itself. That's quite nice. Any questions before we continue breaking things down a little further? All right. And so I said that this has to do with normal cones, right? And really it's supposed to be a conversation about normal cones and faces, right? The original questions we had were, how do we certify optimality? We got normal cones. The second question was, what's the geometry of maximizers? The answer was exposed faces. So how does the dual body connect these two ideas? Well, it's really about the faces of the dual body, or what I'll call dual faces. So first off, we have this really nice correspondence between exposed faces of our convex body. So in this case, we have the racetrack, and on the right, the dual of the racetrack. The exposed faces on the left are in one-to-one correspondence with the exposed faces on the right. So think about maybe this one-dimensional face here. That will correspond to this zero-dimensional dot over here. And sort of why is that? Well, think about what the dual body is asking for, right? We want to maximize in a direction, and in such a way that our set of maximizers is going to be this face. Well, what set of linear functionals does that give us? It's going to be the ones in this direction, right? And that's it. The normal cone is just a line going up, or a ray going up. So now let's cap that. let's bound that ray. Let's say at distance 1, bound that ray, or not distance 1, but anyways, bound the ray, then that gives us exactly this point. And that's how we get these exposed faces, right? So over here, the dual face is the set of linear functionals that attain their maximum on a face over here. So you pick a face over here, and we ask what linear functionals maximize at that face. That gives us the corresponding face over here. So normal cones really are just exposed faces of the dual body. I mean, I like to think of, since these are obviously cones, I like to think of it as we just have to sort of put lines in appropriate places, but that's the idea. Normal cones are really exposed faces, just restricted of the dual body when we restrict to the dual body specifically. And we can write the explicit formula for dual faces by taking the same definition of dual body, or the dual of a convex body. So we have this inner product of our linear functional with any point But now instead of any point in our convex body, any point on the original face. And we have to set this equal to 1, right? Because these are exposed faces, so this is exactly the hyperplane that exposes the dual face. And you can imagine kind of, this is a good exercise in general, is to look at these two objects and try to sort of visualize what happens as the racetrack, the racetrack is the convex hull of two disks, right? So as we move the disks closer together, and this one-dimensional face, both of these one-dimensional faces kind of shrink, and we end up getting closer and closer and closer to a disk. Well, what happens over here? These curves start to sort of smooth out a little until once our one-dimensional faces become zero-dimensional faces and we just get a disk on the left, we end up actually with a disk on the right. So it's a good exercise. It's a little tricky. It's not, I think, the easiest thing, especially if you are new to this notion of convex duality from this perspective. If you're new to it, it's a little tricky at first, I think, to really be able to see what's happening. But it's a good exercise, I think, to try to force yourself to really see what happens as we deform the racetrack into a disk and what happens to the corresponding dual body. And since the origin is in the interior, what happens if we dualize this object, this convex body? Well, we just get the racetrack back, right? So this zero-dimensional face will correspond to this one-dimensional face in the original convex body. So that's sort of the connection of normal cones with faces and sort of this is kind of the setting in which duality sort of naturally comes up in terms of maximizing linear functionals over a convex body. Let's see. I guess questions before we continue. So we have another example with polytopes, since they have particularly nice duality theory, but before I continue, are there any questions? So there's much more I could say, I think, in general about the dual of a convex body. But it is also helpful at times to consider specific sort of more structured families of convex bodies. Polytopes in particular are always a great place to go to. They are, as we know, the feasible region of a linear program and have been studied and really are very well understood from many different aspects. So what's nice about polytopes and duality is that the dual of a polyhedron will always be another polyhedron, which is really, really nice. That does not, that kind of thing doesn't necessarily happen more generally. So for instance, another nice family of convex bodies that we've seen are spectrohedra. Unfortunately, the dual of a spectrohedra is not necessarily another spectrohedra. It is spectrohedron, excuse me. It is a projected spectrohedron. So the dual, if we expand our family beyond spectrohedra to projected spectrohedra, then duality, then that's closed under duality, right? So the dual of a projected spectrohedra is again a projected spectrohedra, which is nice, but that same statement does not hold for spectrohedra, unfortunately. It does hold for our polytopes though, which is really, really nice. Moreover, there's a really nice element to polyhedra or polytopes with respect to what's called the face lattice. So don't worry about it too much, what that actually is. It's just a way of organizing the faces of polytopes, which are all exposed faces. So when I say faces in this context, I actually mean exposed faces because they'll be the same thing. Where essentially you order the faces of a polytope by containment. So here I have the face poset or face lattice. Lattice just means there's some nice structure that I'm not going to go ahead and get into right now, but there happens to be nice structure to this poset. That's why it's a face lattice. So here we have the face poset or face lattice of the square on the left. And we already saw that its dual was the diamond on the right? So the face lattice says we start with, of course, the empty face. The empty set is a subset, is always a face of every convex body generally. Then here we have some 0-dimensional faces. So these are the 4 vertices of our square. Those are contained, of course, in edges. Each one is contained in 2 edges in this case. So, and so then up here on the next level, we have the 1-dimensional faces. And then, of course, in this case, the 2-dimensional face is the highest dimensional face, and that's just the polytope itself. What's nice about duals for polytopes is not only is the dual of a polytope another polytope, the face lattice is just take the face lattice of your original polytope and flip it. Perhaps it's not so dramatic here because flipping it gives you the same same face lattice, because here we have 4 0-dimensional faces, which correspond to the 4 facets of our dual polytope. If you do the same thing with the cube, you'll get a little bit more of an interesting face lattice for the cube. That's different from the face lattice of its dual polytope. But this process of flipping it, so making your empty set the top element, becoming now the polytope of the dual polytope, and so on, right? So then the codimension 1 facets, the maximal proper faces, then correspond to the dual faces, which are exactly the vertices of our dual polytope, and so on. So you flip the lattice to get the dual lattice, and then that gives you the face lattice of the polytope, which is really, really nice. And it sort of, works because of all of the sort of combinatorial structure of polytopes. So always a nice example to kind of go back to is polytopes. In fact, constructing the dual for polytopes is particularly easy. What we're really saying here, right, is that the facets correspond to vertices. And so one way to get the dual body of a polytope is put points on each one of the facets of our original polytope. And then, of course, polytopes are just the convex whole of finitely many points. So then take the convex whole. It gets you exactly this diamond over here, and that works in general. It'll give you at least the combinatorial dual of your original polytope. So that's really nice. I will continue on with conic duality, but I guess before I get to conic duality, are there any questions?
I have a simple question. So do you have an example in the 3D, in 3-dimensional?
On a slide? Yeah, well, I have on 2 different slides dual bodies, yes, but 3-dimensional dual bodies, but not yet.
Okay, thank you.
It's pretty easy to visualize the 3-dimensional. So take the 3-dimensional cube, right? So just a regular die. And then on each of the 6 sides of the die, we're going to put vertices, right? And then take the convex whole of that. What do we get? We get the octahedron. And in general, this is true, right? So the hypercube, the dual of the hypercube will always be the cross polytope. We can see that here in the 2-dimensional case. In the 3-dimensional case, it's still the same thing. It still holds. So we end up with these 6 vertices, 8 sides as the dual of the cube. So that's one nice example. I don't happen to have it in my slides, apologies, but it's a pretty nice and quick way to see the dual.
Thank you.
Cool. So Let's talk about conic duality. So I'm going to define the dual cone of a convex cone. Okay, so for now, I'm going to have my cone living now in R to the n+1 dimensions. We'll see why in a bit. But so we have some convex cone K, and its dual. I'm going to define it as the set of linear functionals whose inner product with any point in our cone is non-negative. And it turns out, just like the dual of a convex body is a convex body, the dual of a convex cone is a closed convex cone. So if we started with a closed convex cone, biduality once again holds, which is really nice. So we have the dual of the dual is the original cone, assuming we started with a closed cone. Otherwise, we would just have to add closure as the only additional thing. So the dual of the dual is the closure of our original cone. Now, at this point, I have to make a little bit of a note. So I mentioned earlier, and this is always a tricky thing with these kinds of presentations on which definition of duality we should be using. Some literature would have called what I defined as the dual of a convex body to be the polar, right? So I mentioned this at the beginning of the talk, that the definition I had given was the polar, and that the dual was actually the negative of that. What's nice about doing it that way instead of the way I did it is that then, if that is what I had defined as my dual, the negative of our original definition, then this definition of the dual of a convex cone just follows immediately from the same definition, right? So they're actually equivalent ways of writing the dual convex cone if we had defined it in the negative way. So it, depending on what you're talking about, you might want to go one way or the other. I wanted to motivate this by thinking about maximizers and things like that. So I made a choice, and now I have to backtrack on that choice a little bit. But instead of actually changing our definition, I'm just going to give some new notation. I'm going to call C star. So if we started with some convex body C, I'm going to call C star the negative of our original dual. And so just a slight change in notation to help with some things coming up. All right, so dual cones. What are some examples of dual cones? Let's start with the non-negative orthant. Very important cone in optimization, right? Linear programming is all about just optimizing an affine subspace intersected with a non-negative orthant. That is essentially how we get the simplex method, right? Because that's what a simplex is. So very important cone. What is its dual? Well, it is self-dual. Its dual is, again, the non-negative orthant. Now, of course, I'm identifying the dual space with the original space. So please forgive me for being a bit hand-wavy with that kind of notation, but hopefully everyone here is more or less familiar with doing that kind of thing. And so what do I mean by self-dual? Well, let's remind ourselves what this, let's remind ourselves what the dual cone is. Well, it's the set of linear functionals, or if we're identifying the dual space with the original Euclidean space, then it's just the set of vectors such that the inner product with any non-negative vector is, again, non-negative. Right, so a vector A is in the non-negative orthant if and only if its inner product with a non-negative vector is non-negative. That's all I mean by self-dual. The PSD cone, another extremely important cone in optimization, right? Semi-definite programming. It is all about optimizing over the intersection of the PSD cone with some affine subspace. That's how we get a spectrohedron. Again, also self-dual. A matrix is positive semi-definite if and only if. Here I have what's called the trace inner product, which is just take the matrices, multiply them, and then take the trace of the product. If and only if the trace inner product is non-negative for every positive semi-definite matrix. So again, PSD cones are self-dual. Also very, very nice. Perhaps you are interested in, like myself, polynomial optimization. So for another example, consider the following set. So by P sub nd of S, I mean, we're going to take a bunch of polynomials in n variables of degree at most d. So that's what this notation means, right? So collect in the space of polynomials in n variables of degree d, collect those polynomials that are non-negative on some subset of Rn. This can be any subset. If you want, just to simplify things, let S be all of R, and then now we're just collecting non-negative polynomials in n variables of degree d. A perfectly good closed convex cone in the space of polynomials. What is its dual? What is the dual cone to the cone of non-negative polynomials? Well, in order to do this, I'm going to have to define certain types of linear functionals in the dual space. So what linear functionals am I interested in? Pick a point in Rn, so I'll call that P. Then the linear functional I'm interested in, remember this is in the dual space for polynomials, right? So this linear functional LP sends polynomials to real numbers. And how do we define that actual map? Well, we're going to just plug in P. So I'll call these evaluation at P, essentially. So these are perfectly good linear functionals where we're just evaluating at P. Then F, a polynomial F, is in our cone of non-negative polynomials if and only if the linear functional associated to any P in our set S evaluates F to be non-negative. Okay, so maybe this is a bit of a mouthful, especially if you haven't seen this stuff before. All this is saying is that F is in the cone of non-negative polynomials if it's non-negative. If evaluating at every point, it's non-negative, right? So we're just saying a polynomial is non-negative if it's non-negative. But the surprising and shocking thing is that from this, it's a little tricky, but it's not too bad to show that the dual cone is not just the set of point evaluation linear functionals. We take all the point evaluation linear functionals that we've defined in this way, and then we have to take the cone over them. So these are conic combinations of these linear functionals, right? And then also the closure. This is exactly what the dual cone is to the cone of non-negative polynomials. This is a really nice theory. So another really important example in optimization, particularly in polynomial optimization, of the dual cone of non-negative polynomials. There's a few examples. I want to connect this back to convex bodies, and it turns out it's very easy to do. So at times it's helpful to think of things in the world of cones, and at times it's helpful to think of things in a compact world, right? So this is something I think Vera has actually already hinted at or referred to a couple of times. So being able to go back and forth between convex bodies, so remember these are compact convex sets with non-empty interior, and convex cones it can be really, really helpful. Some things are easier in the cone world, some things are easier in the convex body world. So how do we go back and forth between the two? Well, essentially, you can read this line if you'd like, but the idea here is take your convex body. So let's go from convex body to convex cone. Take your convex body, embed it in one dimension higher space, and specifically in the affine subspace where we've set the last coordinate to 1. Then take the cone over that. That gives you a perfectly good convex cone. Right, so here I've taken the square and I've embedded it in a 3-dimensional space and taken the cone over that, right? So then It's everything inside of those extreme rays, right? That's our cone. I'll call that K sub C. And the nice thing about this is that the faces of our convex body C are in bijection with the faces, so one-to-one correspondence with the faces of our cone. Doing this process preserves facial structure. And if we want to go back, right, if we start with our a cone, then we just need to take we set our last coordinate equal to 1, and that gives us a perfectly good convex body. Maybe some caveats on technically what we actually need here, but the idea is we can always go back by slicing our cone, taking a base of it, and that gives us our convex body back. So there's this nice way of going back and forth. And why do I bring this up? Because duality plays really nicely with this process. By which I mean, duality actually commutes with this. Now, this is where the way I define duality is a little bit unfortunate, because I defined the dual body. Remember the C star, let me go back actually. So C star is the negative of our dual body. Okay, so some people would have defined C star as the dual, and this is where that's actually a little bit nicer. But C star is the negative of our dual body. Alternatively, I could have also just defined our dual cone to be less than or equal to 0, and then that actually would have worked with our original definition. But then the non-negative orthant and the PSD cone aren't self-dual. So there's always choices that we have to make in life, and I'm choosing to go slightly back and forth, so please bear with me. But the key here is that if we take a convex body C and then take the cone over it in this way and dualize that, look at the dual cone, that's the same thing as first taking the dual body of our C, except that it's negative, and then taking the cone over that. The dual cone of a convex body is the same as the cone of the dual body. That's really nice. Makes everything really worked really well in terms of being able to think about dual objects either in the cone space or in a more compact space. Either one, really good. And I think that's actually everything I wanted to say in terms of, there's much more we could say about convex duality. It's a really beautiful theory, and there's plenty more to discuss in terms of more properties. So for instance, something I didn't mention is that if you have containment of convex bodies, then dualizing reverses the containment, all of these properties and things. There's plenty more to say. But I wanted to spend a little bit of time talking about a couple of topics where these dual objects actually appear in more recent work. So before I get to that though, are there any questions about the sort of background that we've covered today? Hopefully that means it's clear and not horribly opaque, but
yeah, everything is very clear. Just responding so that you know that not everybody is sleeping.
Thank you, I appreciate that. I appreciate that very much. Good. I'm glad. Usually it means it's either clear or very unclear, but I'm glad it's clear so far. Good. So in that case, I want to switch gears a little bit and just talk about two slightly different topics, and but that these convex bodies actually appear, that I think are just very interesting and nice. So the first is has to do with lifts of convex sets. So again, there's a bunch of text on here, but really the picture is the most interesting thing, because what I mean is, suppose we have some convex set, right? So here I have the square again. And I'm interested in this context, finding some higher dimensional object that projects to the square. So here we have a picture of the elliptope, the 3 elliptopes specifically. So this is the PSD cone intersected with the affine subspace to find where the ones are on the diagonal. So a very nice spectrohedron, sometimes affectionately called the samosa. So the square under the right projection is in fact a projection of the 3 elliptope. So another way to say that is the 3 elliptope is a lift of the square. In this case, because the affine subspace we're using intersects the PSD cone, we say it's a PSD lift because it can be written as the projection of the PSD cone, that's our cone K in this text, with some affine subspace. Why would we be interested in lifts? Because optimizing over the object upstairs, the higher dimensional object, the lift, is the same as optimizing over the downstairs object, the lower dimensional thing. And now you might ask, well, why would we want to go to a higher dimensional thing? This might be more complex, or it's higher dimensional, so it's harder to see. But if we have a more compact or a nicer or an easier to work with description upstairs, suddenly optimizing the upstairs object, the higher dimensional object, might actually be easier. So knowing whether such a lift exists and what that lift is very, very important in optimization. And so again, we say that an object has a K lift for some closed convex cone K if we can write that object or that convex set as the projection of a slice of that cone. In this case, this would be a slice of the PSD cone, and our square can be lifted to or written as the projection of a spectrohedron. So how does duality play a role? It's through cone factorization. So there's a lot of text here. Bear with me, I'll try to kind of highlight the ideas and where duality sort of pops up. But let me kind of go through this background and this setup. So we're going to start with an operator S, where the inputs are vectors in Rn, and then vectors in the dual space. And this maps to elements in R, and is specifically defined by 1 minus the inner product of our 2 vectors. The slack operator is the same operator, except instead of all vectors in Rn and all vectors in the dual space, we're actually going to restrict ourselves to the extreme points of our convex body or our convex set generally, and the extreme points of our dual body. So the slack operator is this, but with the domain restricted to extreme points of our convex set and extreme points of the dual of our convex set. All right, so we have the slack operator, and the question is the slack operator K factorizable? That's the first question we want to answer. So what does that mean? It means that we can factor our slack operator into these 2 maps, A and B. All right, so we can write our slack operator as the inner product of A of X and B of Y, where again, A sends elements, extreme points of our convex body to our cone K, right? K factorizable, cone, so our upstairs cone, and extreme points of the dual body to the dual cone. So slack operator is K factorizable if we have such maps and they satisfy, and really we can factor our slack operator in this way using these maps. Good. It turns out that I'll sweep some conditions under the rug essentially, but a convex body has a K lift if and only if it is K factorizable. So that's not exactly what's going on here, but this theorem here, by I'm going to pronounce his name wrong, apologies, Guave, Perillo, and Thomas, essentially proved that. There's a little bit of a caveat, so there's a little bit of a technical term for what a proper K-lift is, but it's, it's a minor thing. But if we restrict to particularly nice cones, such as the PSD cone, then a convex body has a K-lift, or in this case a PSD lift, if and only if the slack operator is K-factorizable, or in the corollary PSD factorizable. So that's really nice, right? We can find this lift for some cone using this slack operator and essentially mapping through the extreme points of our convex body and the cone K and the extreme points of the dual body and the dual cone K. This is a really nice theory. There's plenty more to say about this. Let me just say that this is a generalization of a theorem that was already known for polytopes specifically. This is back in 1991 by Yanakakis, which essentially said that a polytope has a polytopal lift if and only if the slack matrix, which is essentially the same thing as the slack operator but for polytopes, has a non-negative factorization. So this is the same. This is a specific instance of the theorem down here. The K, our cone, in the polytope case is just going to be the non-negative orthant. And then our slack operator turns out to be a matrix, which then you just need to be able to factor into two matrices that have non-negative entries. So if that's possible, then your polytope you started with has a higher dimensional polytope it comes from, like this hexagon being lifted to this five-sided three-dimensional polytope. So they were able to generalize this to other things, which is really, really great. In particular, it gave us a way of thinking about lifting polytopes to spectrahedra. So something that they discuss are what's the smallest PSD cone that, given some polytope, what's the smallest PSD cone that we can lift it to? And we can figure that out using the slack operator. Really, really cool stuff. And again, this isn't meant to be a deep understanding so much as just here are some cool things that you should go Google and look up later. Good. So I think I have a little bit of time, and so I'm going to actually discuss a kind of completely different thing that has, but where duals and duals appear. So this comes from current ongoing work that I am doing with a couple of collaborators, where our question is a little different from what we had in the cone factorization setting. So in the cone factorization setting, we started with some object downstairs and we asked, can we lift it to a higher dimensional object? Now I'm going to ask something else. I'm going to start with some higher dimensional object, which still should be the intersection of a convex cone with an affine subspace. Right? So think the PSD cone intersected with an affine subspace, so a spectrahedron, or the non-negative orthant intersected with an affine subspace, whatever your favorite cone is and your favorite corresponding affine subspace. We start with that as our upstairs object, and then some map A, we project it down. What is the facial structure of the thing downstairs? Right, so we have some linear map A, and some convex body upstairs, which is the intersection of a cone and a linear subspace or affine subspace. What is the facial structure of A of C? So for example, here, this is the dual of the three elliptope. So we saw earlier, this is the elliptope. Again, the PSD cone intersected with the affine subspace of ones on the diagonal. Here, we have a projected spectrahedron. So this is not a spectrahedron, but it is the dual of a spectrahedron, specifically the dual of the three elliptope. And it turns out that this is the linear image of the spectroplex. The spectroplex is essentially the same thing as the simplex for the non-negative orthant. It is a base, it's the canonical base of the PSD cone, the trace one positive semi-definite matrices. So the dual of the elliptope turns out to be, can be written as the linear image of a spectroplex. And so given such an object, right, how can we understand the facial structure of this thing? Well, we were able to show, so there's a whole setup up here that kind of gives you how to actually construct these things. But the key here, what I really want to show is this theorem with Venkat Chandrasekaran and Amy Weeb. So this is ongoing work that we have been doing. So again, start with an object upstairs, right? C is your object upstairs. If you start with a face of the thing upstairs and you map it down, is that an exposed face? It doesn't have to be. In general, right, if we project things down, faces might get mapped to the interior of your object. We don't know. Of course, faces downstairs always come from faces upstairs. But if we start with a face upstairs and we map it down, is that an exposed face of the thing downstairs? It is, if and only if 0 is in the interior of in the relative interior of B star of F star K. Okay, what in the world is going on here? Here's what we do. We look at upstairs. We look at the face that we're interested in upstairs, right? We're asking if the thing downstairs is also a face. Dualize that face. Take the dual of that face upstairs. So that gives you a new convex cone or convex body, depending on which way you want to do it, because remember, cones and duality commute just fine, so it doesn't matter which one you go with. Map that downstairs with this new map B star, which I'll explain in a second. Is 0 in the relative interior? Well, then your face says, then you have a face downstairs. And this is an if and only if correspondence. So what is this B star map? Well, first we start with the A map, right? Remember, our object downstairs is A of C. And I'm going to append to it the inner product of A and X, which is just, this is the affine subspace defining the convex body upstairs. And that I'm going to call that A tilde. So this is a linear map, but now going from Rm to Rd plus 1 dimension higher. Take the kernel of that map and find a basis. So let's say B1 through Bk is a basis of that map, a basis of the kernel. Then B star is a map from the dual space, or the dual space upstairs to some dual space downstairs, where any dual vector we apply to each one of these basis elements. So it's just another linear map, but in the dual space. If you're very, 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 very clever and know quite a bit about polytopes and understanding the facial structure of polytopes, you might actually recognize this as essentially Gale duality. So this is for polytopes, in the very special case of polytopes, where the cone upstairs is the non-negative orthant. The base of that cone is going to be the simplex, which is self-dual. So when we look at this B map, we're really just, we don't have to switch to the dual of the simplex because it's just the simplex again. So that's really nice. Then this is exactly Gale duality. And so what we've done is generalize Gale duality for polytopes to convex bodies more generally. And here is the dual of the elliptope on the left, and its corresponding Gale diagram as the image of this B star map here. And again, the idea is just to be able to reason about the facial structure of the thing on the left using the object on the right. So how do we do that? Well, we'll take a face upstairs that happens to map to this face here, right? So the dual of the elliptope has these flat disks, the two-dimensional faces. Then we go upstairs you take the dual object and then map it down to the Gale diagram using the B map. And what you should get is the convex hull of this triangle. 0 is in the interior, in the relative interior. So that means this thing over here is a face. And that's an if and only if correspondence. And the idea is that this can be useful to take higher dimensional objects that might be difficult to understand and reason the structure of, lift it slightly to an even higher dimensional thing whose face we do know things about, and then project it down to this lower dimensional Gale diagram that helps us understand the facial structure. So here we have this 3-dimensional object, but the Gale diagram, which gives us all the information about exposed faces, is 2-dimensional. For polytopes, this is typically used for high-dimensional polytopes with few vertices, so that you get this lower dimensional Gale diagram that helps you think about the facial structure. But yeah, the nice thing is this actually turns out to generalize. This is some recent work that we've been thinking about that I think is really cool. It gives you another reason to sort of understand not just the dual body of something, but the dual cone as well. And that's it. That's what I have. Apologies, I think I went over time a little bit. But yeah, thank you so much for letting me speak on the things that I found interesting. Are there any questions?
Thank you, Isabelle, for a very nice talk. So any question? Vera, yes.
I think Nadia raised the hand at the same time, but okay, since you picked me, I find the last slides really, I mean, it was an amazing talk. I think I knew a lot of things in the beginning, right? But the last things were really interesting to me. I'm wondering if I give you a convex set, even something like compact convex set that is not facially exposed, can you then produce a convex set that is facially exposed and can be the original set can be obtained as a projection of that set or as some kind of a linear image of that set? So I have a set that is not facially exposed, but I'm asking you, give me a facially exposed set, right? That I can apply linear mapping to and get my not facially exposed set.
Right. Yeah, so this is, so the idea is, can we lift something that has non-exposed faces to something that we know is facially exposed only, right? Yeah, that's a good question. And I don't know that I have a general answer for this. As you actually mentioned in your talk, one of the reasons we really like spectrohedra is that they are facially exposed, right? So that's one of the reasons lifting, specifically looking for PSD lifts, is very helpful. It's not just that they're exposed, right? We have a full, proper understanding of the faces of the PSD cone. In fact, if we can lift, so this is lifting to a spectrohedra. On the other hand, I mentioned that the dual of the elliptope is the linear image of the spectroplex, and the spectroplex, the facial structure is in 1-to-1 correspondence with the PSD cone. So we really understand that facial structure, right? So I guess my answer is I'm not sure in general. What this cone factorization does is you can see if there is a K lift for a given cone K, right? So if you want it to be the image of a slice of the PSD cone, then you can set up these, you can try to find a factorization of your slack operator that specifically factors through the PSD cone, and then yes, then you have a facially exposed lift. But you have to choose the K first. You have to choose that cone first, and hopefully you can choose a nice cone that you know a lot about. To do that generally, to just be like, oh, let's hope for a cone that's facially exposed, I don't know. I don't actually know any way to do that.
Cool. Makes sense.
Yeah, I hope that answered your question.
Thanks.
So any other questions?
Sorry, can I ask a question also?
Yes,
Yeah,
please.
Yeah. Okay. So also actually about slack operator. So first of all, I'm actually new to this area. So you said that these two operations, they are equivalent in the sense that if one exists, it's if and only if another one exists, right? So the k-lift and the factorization of the slack operator. So, but to me, both these operators are actually difficult to it's difficult to check if it exists, right? So both of them. Yeah, okay. So it's not that you move the burden from one to another one, right?
Yeah, I mean,
Okay.
in general, this can be a very difficult problem. I agree. I think even if at least as far as I know, the last I heard, we don't have like a systematic way of finding the K factorization. Yeah, so this is not an easy, necessarily an easier problem.
Okay,
right.
okay, yeah, thank you.
Yeah. I would say that maybe for certain types of cones, it's not too bad. But even then, even the PSD cone actually already, a really nice cone, we know quite a bit about it, but a PSD factorization already isn't necessarily easy to do. Yeah.
Yeah, thank you. Thanks.
Any other question from the audience?
Maybe let me mention one more thing, which is that
Okay.
along with these authors, I believe James Sanderson, who is in Australia, is also working on these things and might have more certainly would have more information than I do, and certainly would be interested in talking about those things too. So let me just throw that name out as well.
So any other questions, comments? Well, if not, then we thanks Isabelle again for a very nice and interesting talk.
Thank you so much for having me. It was
Thank you.
a delight.
Thank you.
Thank you.
Thank you very much.
Bye.
Thank you so much. Bye.